Welcome back to the channel. Today we are starting our comprehensive Java collections mastery series. In the first video, we are diving deep into ArrayList, vector, synchronized list, and copy on write ArrayList. We'll explore each implementation's thread safety model, performance characteristics, and real world use cases. By the end, you will understand exactly when to use each one and how mastering these four list implementations will help you build reliable thread safe applications without guesswork. Let's get started. Let's begin with ArrayList, the most commonly used list implementation. ArrayList provides a resizable array implementation of the list interface. It's designed for single threaded application and read heavy scenarios where maximum performance is required. Internally, ArrayList uses a dynamic object array that maintains element insertion order while allowing duplicates and null values. Now, regarding its behavior under modification, so ArrayList implements failed fast iteration model, meaning iterators through concurrent modification exception. What is concurrent modification exception? So it occurs when a collection's structural modification count changes unexpectedly during iteration. ArrayList maintains a mod count field which incremented on each structural modification. So iterators store this value when created and compare it during operations. A mismatch throws the exception, preventing undefined behavior. If the list is structurally modified during iteration, this makes it unsuitable for concurrent modification without external synchronization. Here is the array list in single threaded context. We create array list, add element, iterate safely since no concurrent modifications occurs. The standard for each loop works perfectly here, but would throw concurrent modification exception if we modified the list during iteration without using the iterator's remove method. In terms of performance, ArrayList offers O of 1 time complexity to access by index, O of n for searching, and O of 1 amortized insertion at the end, though insertion at specific position requires O of n time complexity due to element shifting. Now let's examine how ArrayList handles memory. Memory-wise, ArrayList provides compact storage with contiguous memory allocation, storing only object reference plus array overhead. When capacity is exceeded, ArrayList grows by approximately 50% of its current size, starting with default capacity of 10 elements. This resizing strategy balances memory efficiency against performance cost of frequent reallocations. Now let's move to vector, ArrayList thread safe predecessor. Vector represents a legacy synchronized resizable array implementation that was Java's original thread safe list. While largely superseded by newer alternatives, Vector still appears in legacy code bases where simple thread safety is needed without performance optimization. Like ArrayList, Vector maintains insertion order, allows duplicates and nulls, and uses dynamic array internally. However, Vector's thread safety comes with significant cost. Vector achieves thread safety through fully synchronized methods, meaning every operation acquires a log. This provides thread safety but creates substantial performance overhead in multi-threaded scenario. Its iteration behavior remains fail-fast, but unlike ArrayList, vectors requires external synchronization during iteration to prevent concurrent modification exception. Vector usage resembles ArrayList but provides built-in thread safety. However, notice that even with vector, iteration requires external synchronization to be truly thread safe, when other threads might modify the list during iteration. This is common pitfall with vector. Developers often assume full thread safety extends to iteration, which is not true. That's why we had to wrap it under synchronized block. Let's compare vectors performance characteristics. Vector shares the same big O time complexities as ArrayList, O of 1 for access, O of n for search, O of 1 for amortized append, and O of n for insertion or deletion in the middle. However, actual performance is significantly slower due to synchronization overhead. Vector's resizing behavior differs by default. It doubles capacity when it gets full, though this can be configured via the capacity increment constructor parameter. Now let's examine a more flexible approach to thread safety. Synchronized list provides a wrapper that adds synchronization to any list implementation. This approach offers great flexibility than vector, allowing you to add thread safety to existing list implementations like ArrayList or linked list. The wrapper synchronizes on mutex object, providing thread safety at the method level. However, iteration requires careful handling. Similar to vector, synchronized list exhibits fail-fast iteration behavior. The critical difference is that iteration requires explicit client-side synchronization. You must manually synchronize on the returned list during iteration to prevent concurrent modification exception and ensure thread safety during traversal. This places more responsibility on the developer but offers greater control. With synchronized list, we explicitly synchronize during iteration. The synchronized block ensures no other thread modifies the list while we iterate. This pattern is essential for thread safe iteration with synchronized list and vector. Notice we synchronize on the list object itself, using it as the monitor lock. Let's consider performance implications. Synchronized list inherits the performance characteristics of the wrapped list implementation while adding synchronization overhead. This means O of 1 access for array based list or O of n for linked list plus locking cost. Memory usage includes the wrapper object overhead in addition to wrapper list memory footprint. It's a general purpose solution when thread safety is needed for existing list implementation. Now let's explore a modern lock-free alternative, that is CopyOnWriteArrayList. It represents a sophisticated thread-safe variant optimized for read-heavy scenarios. It employs a copy on write strategy where modifications create a fresh copy of underlying array. This design makes it ideal for observer pattern. For example, consider event listener lists where listeners are registered less often and events are broadcasted frequently. And other situation where reads vastly outnumber writes. This unique approach affects iteration behavior. Copy on write ArrayList provides thread safety without explicit synchronization by using volatile array references and ensuring all mutative operations copy the underlying array. It features weakly consistent iteration semantics. Iterators work on a snapshot of the array taken when the iterator was created. This means modifications during iteration don't affect the ongoing iteration. Copy on write ArrayList simplifies thread safe iteration. Hence, iteration requires no external synchronization because iterators work on a snapshot. This makes it ideal for scenarios like event listener management where iteration is frequent and modifications are rare. Notice how we can safely iterate while other threads potentially modify the list. Copy on write array list enables truly concurrent modification pattern. In this example, thread 1 iterates through the list while thread 2 modifies it concurrently. Because copy on write array list uses snapshot iterators, thread 1 continues iterating over its snapshot while thread 2's modifications create a new array that becomes visible to subsequent iterations. However, this design has performance trade-offs. Read operations in copy on write ArrayList are exceptionally fast with OOP 1 access and no locking overhead. However, write operations are expensive at OOP and time complexity due to array copying. Plus, the memory overhead of maintaining two arrays during modification. This makes it suitable only for scenarios where writes are infrequent compared to reads. Let's discuss critical best practices. First, never modify a collection directly while iterating over it, except through the iterator's own modification methods. Second, always synchronize the entire iteration block when using synchronized collections. Individual operation synchronization doesn't protect iteration. And last, consider iteration cost with copy on write array list, as each iterator creation makes a snapshot copy of entire array. And here is common mistake with synchronized collections. This example shows a typical mistake with synchronized collections. A developer assumes the synchronized list provides thread safe iteration, but it doesn't. Only individual methods are synchronized, not the iteration sequence. This code can throw concurrent modification exception in concurrent environment. Hence, we need to synchronize entire iteration process. Finally, let's consider capacity planning. For ArrayList and vector, specify initial capacity when you know the approximate size to avoid frequent resizing. Each resize operation copies all elements to new array, incurring OOP and time complexity. For copy on write array list, consider that each modification creates a full array copy So write operations become increasingly expensive as the list grows. So let's review key takeaways. Each list implementation serves specific need. Choose ArrayList for single-threaded applications where maximum performance is critical. Select vector only when maintaining legacy code that requires its specific behavior. Use synchronized list when you need thread safety for existing list implementations and can manage synchronized iteration blocks. And at last, opt for copy on write array list in read heavy, rarely modified multi-threaded scenarios like event listener management. The choice depends on your specific requirements for thread safety, iteration behavior, and performance characteristics. Always match the implementation to your actual usage pattern rather than defaulting to familiar choices. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.